Okay, here we go for part two. We want to take the derivative of this thing. This is a big old chain rule, right? We got g at x equals 7 to some function involving x. And so we're going to need the chain rule. So the derivative of the mum is 7 to the exponent whatever ln 7, right? Well, the whatever, the baby stays inside. And then I take the derivative of the baby, right? The derivative of the mum is just this ln 7 sort of fudge factor that we figured out in the first video, and then we multiply by the derivative of the inside part, which is just 1, and then the 2 comes down minus 6x. And that's it. That's just the derivative. Fantastico. When does that terrible function have a horizontal tangent? Ooh, and you can just feel it coming. Graph that. Find where it's concave up, all those fun things. When does it have a horizontal tangent? Well, we know horizontal tangent happens when f prime at x equals 0, and so let's do the derivative. Well, I've got a function and another function. I think this is a chain rule or a quotient rule question. This is a bit nasty looking here. Let's change this form a little bit. The square root, remember, in exponents is to the exponent a half. And so I'm going to actually write that as 5 to the exponent x over 2. That doesn't look nearly as bad as the square root of 5x, where that would be a chain rule that goes with our quotient rule. So let's think of f at x as like that. Can I write that down there? So this isn't nearly as bad, I don't think. Derivative of the top is just whatever that is, right? And then the derivative of the inside part, which is the derivative of the top, rather, has the ln of 5 in it. And then the derivative of the inside part, the derivative of the baby, is a half. And then write down the bottom, right? I write down the bottom, which is x minus 1. Subtract, write down the top, derivative of the bottom, which is just 1, all over the bottom squared. And this is pretty nasty. Is there some simplifying I can do? There certainly is. Notice that this thing right here, change the color, is a common factor, right? So I'm going to write that out front, change my color back. And what do I got left? I've got ln of 5. These are just numbers, by the way, and if you ever got sick of seeing ln 5 times a half, you could just jam that into a calculator, but I'm okay seeing it like that. Hopefully you are as well. And then when I take this out of this term, I think I'm just left with 1 all over x minus 1 squared. And that's the derivative in nice simplified form. Isn't that beautiful? Well, horizontal tangent is we want to set this thing into to equal to 0. So horizontal tangent is when that's equal to 0. And so I want to solve this. So I got this big long mess that's not only a rational function because of the divide, but it's also an exponential function because of this, right? Well, we know rational functions, since this is all one factor, I multiply by x minus 1, and as long as x cannot be 1, we can do that, and then I'm left with the top is equal to 0. So therefore, I've got 5 to the exponent x over 2 times that bracket. Big mess. And I suppose I could simplify that, but I'd probably have to use my calculator, and I don't want to do that. Equals 0. Now notice, what do I got? I got two brackets. That thing and that thing. Two factors, rather, that are equal to 0. This is never 0, right? This is some sort of function, maybe like that. You know, it's an exponential function of some sort. This is never 0. So that means there's no solution from this part. If we're going to have a solution, it's going to get from this part. So therefore we say ln of 5 x minus 1 minus 1 equals 0. So now we got to go about starting to solve this thing. So the 1 goes on the other side. Multiply by 2 and divide by ln 5. Can you see how those would be the next steps? Multiply by 2, divide by ln 5. Multiply by 2, divide by ln 5, then add 1. And if you jam that into a calculator, you get that that's about, assuming that I did this correctly, 2.24. So on this graph, when x is 2.24, we should have a horizontal tangent, a minimum or a maximum, perhaps. An application. Example 3, Ferd's account has $500 in it, and it's growing by that much, compounded quarterly. And we're asked to write a function to represent the amount in the account after X months, and then calculate and interpret A prime at 16. Well, this reminds me of the optimization question. We weren't asked necessarily to find the maximum amount in the account, but maybe some other function, maybe some other case we could, or maybe we would solve a related rates question or something like that. Is that possible? Are we going to have to do that in this chapter? Yeah, possibly. So, I mean, everything that we've done, we can do with exponential functions. Curve sketching, we already talked about. Is that coming? Yes, it is. But anyway, write a function to represent the amount in the account after X months. Really, it's just this finance formula from grade 11. We need to fancy it up a little bit. What do we got? We got the P is a mess here. P is 500. And the interest rate is 8% compounded quarterly. So that means I divide the interest rate by 4. But notice there is some nastiness now because X is in months. So how do I go from the number of months to quarters? Because N has got to be the number of quarters, right? Well, it doesn't take too much thinking to, if it was 12 months, that's 4 quarters. Divide by 3 is how we get from months to quarters. And what else do we need to know here? I we got, and then A is our function, right? So we've got a function that models the amount in the account after X months. Lovely. And then it asks us to calculate the derivative and interpret it. No problem. Here we've got a function. Take the derivative. All right. The function itself, the constant sort of hangs out front. The derivative of an exponential function is the function itself times the ln of the base. The base here is that nasty number, and I'm getting rid of some of this stuff because it's getting in me. Well, that was annoying me. Let's get rid of that. So that's the derivative of this. Now we got to take the derivative of the inside part, right? The inside part is x over 3, so I multiply by a third. And that's it. I mean, we could tidy up the number parts. These are all number parts, so I suppose if we wanted to, we could put all the number parts out front. But here we just need to calculate, right? It wants to say, calculate what this is. So, well, warm up your calculator. Fire it in there. I got, when I did that, jam that into my calculator carefully. Remember, using the ln button, not the log button now. You might want to put your exponents in brackets there so you can go 16 divided by 3, or a fraction button if you've got that on your calculator, and try and put that in. And you can tell me next day whether I was right or not. I got 3.67. So what is that? 3.67 years, 3.67 months, $3.67. Well, remember, this is a rate of change. what's going up? Well, the amount in the account. So that's dollars per time unit, per month, or per quarter. Per month or per quarter? No, X is in months, per month. So that means after 16 months, Ferd's account is increasing by $3.67 per month. And that's the interpretation. That's it for today. There's your homework. Have funsies with it.